Looking into the agenda briefly, as you can see, there are six main there are six main speeches slots today. I will talk briefly about the FLEXYNETS project, just to introduce what we are doing and what is the this webinar about. And then we will go into the main technical talks by Daniel Trier, Plan Energie, Philip Geyer, coordinator of the h-disnet project, and then by Dirk Pietruszka and Johan Desmet from Any System Vito, again talking about control in these district heating and cooling networks. I will conclude the morning by talking about the financials of these solutions and about business models that can apply to these, say, district heating and cooling networks. As I said, we are going to take your questions at the end of each of these speeches. We agreed with the speakers that they are going to talk, the slot will be something like 15 minutes, and then we will have 5 minutes at the end of the speech to reply to your questions again. Okay, sorry for this delay, for these problems. So shortly about FLEXYNETS. FLEXYNETS is a small Horizon 2020 project that has to do with what we call fifth generation low temperature district heating and cooling networks. The partnership is also very small for usual Horizon 2020 partners, with a couple of partners by academy, us, URAC, and the Hochschule Stuttgart, and with the other 4 partners from industry, from different industrial sectors, from renewables to control to planning of district heating networks. Why we call the kind of networks we work on fifth generation is because, on the one hand, one of the topics, one of the specific objectives we are working on is to reduce the transportation losses as much as possible. And again, to do this, what we are studying is networks that operate in between 10 and 25 degrees C of the distribution medium, which is water for us. We will see different approaches in the next presentations. And again, what we are doing compared to traditional networks, but also with respect to fourth generation networks, is to look into how to integrate multiple energy generation sources. Not only few, for example, industrial waste heat, or specific sources like in fourth generation solutions, but as many as possible generations, both coming from waste heat and renewables. The other main topic we are working on is how to exploit the thermal capacity of the network, both in terms of the water, and therefore in inertia that is included into the pipelines, but also by using say thermal storages that are say set up at central level, like large storage pits that are normally used for example in solar district heating networks, like in Denmark, as you if you know the solution. But also looking into decentralized local local storages that are set up in each of the customers' buildings. As you can imagine, as we use transportation, a transportation medium that is at these neutral temperatures, as we call them, we cannot use it. We cannot use the thermal energy directly into the customer site, but we need, say, heat pumps, basically to rise the temperature from the network temperature to the user's useful and comfort temperatures. And then again, if we couple all these issues together, so multiple energy generation, storage capacity, heat pumps all together, you can understand that the main focus of the project then comes onto the control strategy, onto how to manage the network itself in a proper way. From the approach point of view, we didn't invent really something new. We have taken from the water loop concept that is quite a state-of-the-art in the tertiary and in the retail sector, in which you have one low-temperature water loop that is running all through the building, and then you have single rooms or say single stores, heat pumps that can take energy from the loop or can feed energy, waste it into the loop. And this way the fed and the drawn energy, thermal energy, somehow balance out into the loop. What we are doing now is to transfer this concept from the single building into the living environment, to the quarter and to the city level. And for doing this, what we are doing, and in particular you will see Plan Energy is doing, what we are doing, we are trying to understand what are useful topologies and sizes of the pipelines to distribute this low temperature thermal energy. And again, we are moving from, we are evaluating typical, say, topologies that are usually exploited in third and fourth generation networks, but we are looking also into possibly into using only one pipeline in the network. Next step is then to understand how to connect buildings from the production side and from the final customer, from the user side, to the network itself. And again, from the customer side, as I told you, we need some kind of a heat pump to rise the temperature level from the network to the customer to the needed level by the customer. So again, from the customer point of view, if this is representing the network, again, we are studying or we are designing solutions or substations that include, for sure, a heat pump and a storage, but also solutions that include a combination of heat pumps and gas boilers, as you can see, in order to not concentrate only on new build, on new buildings with an high energy standard, but also to address, say, the entire built environment, taking into consideration, therefore, also all buildings. On the other hand, we are looking into the production side. So we are looking into how we can recover waste heat from, say, different sources available along in the built environment, along the path of the network. Like they could be data centers or refrigeration systems in supermarkets, but also how to harvest renewable energy sources. I don't want to go into much details in this, but just highlighting I just wanted to highlight the activities for now. Next step, again, as I said, is to understand how to control all this network. As you can imagine, once you move from the typical structure with one big thermal plant that is distributing thermal energy to many customers, into a situation when you have many producers with a production timeline which is not always say predictable or not always controllable at central level, you need to have a solution to or you need to have a much more flexible control solution at central level. And this is what we are trying to do with the company Enisis, and that is developing hardware and software for this purpose. And again, if we try to make a long story short, basically what we are trying to do is to understand how to use thermal storage capacity in different ways, as I explained you at the beginning of my presentations. And when we talk about this, the main activity, and when we talk about integrating renewables, for example, like solar thermal, and the solar thermal source, we are also trying to understand how to forecast and predict, say, the thermal energy that is going to be fed into the grid in the next hours. Finally, the last point, the last activity we are carrying out is this financial assessment and business model assessment, because most of the time, from the technical point of view, solutions are feasible, but when you try to go into the financials, then you discover that barely they can land on the market, so to say. And then beside or in parallel with the technical activities, we have also this complementary task, which is about understanding which energy sources are most suitable to be integrated in this kind of networks from an economic perspective. What price should be paid for the energy that is fed into the grid, and again, what are the kind of business models and incentives that can be applied to the customers and producers that integrate that are connected to the network itself again. As I was saying, I don't want to enter into the details of the different activities. As I explained, the partners, you will see 3 presentations about the topics I spoke about briefly now about. And again, as I was saying, this is a joint webinar, meaning that I presented the FLEXYNET point of view on cold district heating networks, integrated different energy sources. But again, this morning, you will see also different perspectives by the project Storm and by the project h-disnet. And that is why we wanted to have them on board today. This is it from my side. I think we are already a bit behind schedule, so I would move forward really quickly, and I would hand over to the first speaker, which is Daniel Trier by Planenergy Denmark.
Thank you very much. As mentioned, my name is Daniel Trier. I come from the Danish consulting company, Planenergy. We're specialized in planning of intelligent energy systems, integrating different components and sectors to optimize efficiency and increasing the share of renewables. So in terms of the agenda for today, let me see if I can modify this or change the slides. Otherwise, I'll have to see if, yeah, now I think I have controls. So, let's say, sorry, 1 second. Am I able to flip to the next slide? There you go. So the scope of the analysis that I will talk about is the network layout within different urban environments, and this subtasks. Sorry, this task is sort of split into two subtasks, where one being investigating which type of urban environments are we talking about, and the second part is the design of the network itself. So moving to the first part of this analysis regarding the different towns and, let's say, settlement typologies, meaning the different part of the towns, which can be very different from the average of an entire town. So in order to test the FLEXYNETS concept in different contexts, we've analyzed different towns and not only the towns as a whole, but actually also split in different sections of the towns. And this is used to understand how FLEXYNETS can be feasible, applicable for different urban environments and in different locations. And this first part of the analysis has been carried out by extracting data from different databases and by means of GIS-based software, which I will explain about in a minute. As mentioned, we're not only looking at average values for an entire town, but since one of the ideas behind FLEXYNETS is that it should be easily scalable, we are also looking at a small part of the town, and then we can always expand from that. So the methodology has been, as I'll explain now, first of all, we split the town examples in 4 different categories. And as you can see here, in small towns, medium towns, large towns, and then bigger cities with more 1 million inhabitants. And the approach is sort of semi-automatic, which means that we have combined different databases. One of the databases is municipality planning, which defines the typical use of a certain area, and a second, let's say, second layer added on top of that is a so-called heat atlas, which defines the demand on an annual basis for each building and the location of that. So combining these, by combining these, we can know exactly how the demands are distributed over the towns and in the different typologies, sectors of the towns. I will show an example in a minute. So these type of typologies that I'm talking about is, as shown here, split in 4 different main categories, and within these even subcategories are included. So we're not only talking about, this is a residential area, but we're also looking into, is it a suburb, or where the households are distributed a lot, or is it a downtown high-dense area with high-rise buildings, and so on. So this way we have these typologies we have applied to all the different part of the towns, and one example here is Sønderborg, a Danish town of approximately 27,000 inhabitants, covering an area of approximately 13 square kilometers. The red area is just what is defined as a town area, and applying the typologies I explained about before gives us this result, where we can see that the center of the town is the dark blue one on the lower left part of the town area, whereas the yellow ones are the industry areas where we could expect to see some sort of excess heat facilities or availability. So, and on top of that, we apply the heat atlas defining the heat demands for every building in this town. And the outcomes of this is that we have analyzed a total of 15 different towns and cities, and then each disaggregated by means of the 10 different settlement typologies, and then defining the heating and cooling demands and the share of each typology in the different town sizes. And this gives us then either entire towns to investigate further to analyze the FLEXYNETS concept for, or part of the towns. As mentioned, we could choose specific typologies to investigate. And as we have gone through this list of different towns, we see similarities within the country specifically, but actually there are great variations between different countries. And it seems like this is not only weather conditions that affects the differences in demand, but also that insulation levels are typically higher in northern European countries, which somewhat compensates for the colder climates. And the amount of older non- or low-level insulated buildings is also very different from country to country, and even from town to town perhaps. And also, what does high-rise buildings mean? In some countries, a high-rise building would be 3 or 4 stories, whereas others would define that as 7, 8, or even more. So the high-density areas might even be very different from country to country. So this just tells us that when designing the district heating and cooling networks in practice, it's very important to take the local conditions into account. Moving on to the next part of my agenda in terms of the network design. This is the structure of the network design approach, where we combine conventional district heating with the FLEXYNETS concept, because we feel that even though we might identify suitable configurations to make the FLEXYNETS concept feasible, we would like to avoid the question arising that why don't you just go for a conventional district heating in this area? It might be even more feasible. So in order to be ready for that kind of answers, or let's say in other words, defining where is FLEXYNETS more feasible compared to district heating or conventional district heating or individual heating. So in order to be ready to answer that, we have compared also with conventional district heating network layouts. And not only this comparison has been made, but also different structures of the network itself, where we compared traditional tree structure, where we have this branches going out from the center part where the supply point is, typically the district heating plant. Compare that as one option with a ring structure where we have a geographical ring throughout the town area, and several smaller branches or twigs sort of growing from that ring. And I will show examples of that in a minute. Here's one case or one overall map of the analysis for Aarhus, which is a town in Denmark with approximately 260,000 inhabitants. And what we did here was taking 2 examples from this town, one example in the outskirts and one example in the city center. So the first case in the Aarhus one is the lower left one in the southwestern part, where we applied a ring structure to make it possible to reach every consumer in this area. And it might be a bit hard to see, but this is just an example of let's say the tree structure where we have centralized supply points and branches to reach all the consumers from that. And similarly, when applying the ring structure, we also need to have branches going from the ring out to reach every consumer. So this kind of comparison between the different structures and as well the different temperature levels in the FLEXYNETS versus the traditional district heating temperature levels. And the second case, of course, is city center. And here we have the purple area is due to the fact that we have the red area as a background defining the town, and then on top of that the dark blue one, which means this is a city center, a high-rise, high-density demand area. So the purple area is sort of the city center, and we applied then the ring structure in different geographical diameters, where we have here a larger one and a smaller one to see also how big should such a ring be. Another case is another smaller town where we have approximately 71,000 megawatt hours in demand in the district heating network that is existing already. And here we then apply also a ring structure to check this. So this is just for you to get a feeling of how we apply this analysis at this point. So checking the feasibility, we compared the different options, and it's very clearly seen that investment costs will affect the feasibility, meaning the network, how much does the piping cost, and the prosumer heat pumps needed to rise the temperature at the consumer side, and so on, and also operation costs, meaning what does the electricity cost to supply the heat pumps at the consumers or prosumers, and also the electricity for the network pumps to circulate the flow in the FLEXYNETS network and also the district heating network. And it's also a matter of market pricing approach, which type of financing options is available, which type of ownership would be possible, which is also something that we investigate in the FLEXYNETS project. So as mentioned, local conditions will have a significant influence on the feasibility, as well as what would be the optimal solution in a given situation. Is there a large cooling demand, meaning is there usable heat sources available from the cooling processes? And these heat sources or other excess heat facilities, how are they located? Are they spread a lot across the town area, which would lead to an increased feasibility for the ring structure, because then a larger number of supply points could be reached by the ring. So it becomes easier to feed in with excess heat to this network. But if you only have one centralized excess heat facility you need to reach, then the ring structure might be less feasible. And what temperature levels are we talking about, and are the settlement typologies uniform or scattered, and so on. So we see a lot of different local conditions affecting what would be the optimum solution. Also, as you saw before, the different, let's say, geographical diameters of the ring structure. Is it a big ring covering a large part of the area that we investigate, or is it only located in the very central part of this area that we would like to cover with the FLEXYNETS concept? Well, that also affects the feasibility, and in general it seems like it's not feasible to place the ring at the very outskirts of this area that we would like to supply, but you should rather place it more centralized in order to, let's say, supply both inwards and outwards with such a ring structure. And also more excess heat available for the FLEXYNETS system makes it easier to compete with traditional district heating. In other words, the feasibility of FLEXYNETS over the traditional district heating might be caused by the fact that you have a lot more excess heat available at the low temperatures. That's what the FLEXYNETS concept needs, compared to the higher temperatures required for excess heat to be applicable or available for traditional district heating. And also a ring structure seems to require a certain amount of excess heat to be reached by the ring, or a more high density area to make it feasible compared to a branch structure. And also, the detailed optimization of the different case will improve the feasibility, whereas so far we have more looked into the initial investigation and comparing different options, and the further work will also be about, let's say, more optimizing the concept. And regarding these next steps, this is a structure mentioned before. Yeah.
Can I ask you to conclude?
Yeah, I'm very missing one slide more than this. So I will just mention that this is not only for this task described here, but we could also add on top of that some further financial costs to optimize for the lowest possible price for heat and cooling at the end. So the next steps will be different storage options also to influence that and optimize that part and combine with this analysis. And also more detailed network simulations will be carried out and different geographical locations will be investigated. So I will conclude on this and give the word back to the organizers at Europe. Thank you very much.
Thank you, Daniel, for taking the timing. Are there any questions to Daniel? I didn't see any on the screen. If not, and again, while we are waiting for questions on this topic, there was a concern on the previous presentation regarding the combination of gas boilers and heat pumps, which could hinder somehow or could reduce incentives applied to retrofitting buildings. I will reply to this briefly. When I spoke about a combination of heat pumps and gas boiler in final customers' buildings, I didn't mean that we are designing these combinations for new build or for retrofitted. Retrofitted buildings or new buildings do not need any gas boilers, as the temperature levels for space heating are sufficiently low as to be served by or driven by heat pumps. The point is that in a real built environment, not all the buildings are retrofitted or new, and based on the actual retrofit rates that we have over Europe, it is not reasonable to believe that our cities are going to be completely retrofitted in the next few years. Tens of years, I would say. Therefore, again, what we thought is that we have to also have in mind combinations of existing gas boilers installed already in old buildings and new installed substations, including heat pumps and storage tanks, and one storage tank. In a way that again the gas boiler, the existing gas boiler, is able to cover the peak loads, the space heating loads, which cannot be covered by the heat pump itself. Therefore, the installation or the connection of all buildings would be made again with the same kind of heat pump substation, which takes also the control of the existing gas boiler to cover peaks, if this replies to you. And then in this case, the incentives shouldn't be, say, affected. hopefully I replied to your question. Going on with the presentation, we have the first, oops, there's another question. Hi Daniel, how do you assume the heat demand of the topologies if there aren't any measured energy consumptions available? Are we simulating or not? Daniel, I don't know if you want to reply to this.
Yeah, I can. I think I can do it fairly briefly. This heat atlas is based on a national database with the building register, defining which type of building are we talking about for every building in the country actually, and the owner is obliged to update this if he changes his supply type. So we have the type of supply and also the average annual heat demand for that. So of course there are some uncertainties because it's not measured demand, but previous investigations on this uncertainty has shown that once you don't go too much into each building on its own, but have an average value for a town area, then it's actually fairly accurate to do it like this.
Yeah, and this atlas is quite typical or quite peculiar of the Denmark scenario, but these atlas are also starting to born here and there in Europe, over Europe, in Germany and other countries. So again, it is not that easy as Daniel showed to get this kind of data over Europe, but it is going to be in the next years. Exactly, very good data conditions in Denmark. Exactly.
Yeah, so let's say the majority of towns investigated are the Danish ones based on these availability of data, but we also include several from other countries to also investigate the differences there. Okay,
thank you, Daniel. Let's try to go directly to the next speaker, Philip Geyer from KU Leuven and the project h-disnet.
Okay, yeah. Thank you, Ricardo, and good morning to everybody. First, I hope my sound quality is okay. You can hear me well. If not, please let me know.
No, very good.
Okay, thank you. So let's start. What I would like to do today is to present you the project h-disnet, Intelligent Hybrid Thermochemical District Networks. That is a small project, 2.7 million euros budget, with 7 partners: KU Leuven, Wargy, small startup from Berlin, TU Berlin, ZHAV, Zurich School of Applied Sciences, and the Sir Joseph Swan Center from Newcastle, and then 2 companies. First, Arubis, largest copper recycler in or producer and recycler in Europe, and Thermoflex, company producing plastic equipment for district networks. Yeah, of course today is not the 15th of May and we are not in Glasgow, sorry for that, but that's the opportunity to make short advertisement. So we are repeating this presentation next Monday in Glasgow, Monday afternoon, and if you're interested, you're welcome to join discussion and workshops there. That's the Euroheat and Power Conference. Okay, so let's move on. Today I would like to give an introduction to the thermochemical technology. That's the main intention, and not to talk about too much details of the project. Okay, so yeah, I have controls. Yeah, it's moving on. So the starting point of applying thermochemical technology in district networks was the observation from that Danish study, I guess you know it, that excess heat from industry is nearly the same amount as heating demand of buildings. So it is only a question of transporting that excess heat to the right location, shift in the location and also shift in time, but this only is, of course, as you all know very well, not so easy. And so the idea of the project is to support this transport and storage of excess heat potential by thermochemical processes, basically absorption and desorption. And that's what I would like to explain today, what you can do in a district network with these kind of processes. So let's start with the basics. Process is the evaporation or the latent heat that is in humid air. So if you have 1 cubic meter water or 1 ton of water and evaporate that, that takes 680 kilowatt hours heat energy. And this amount of energy is usually enough to heat, or 7 cubic meters are enough to heat a 120 square meter low energy apartment 1 year. So that is quite a large amount of energy that is available by that process. And this kind of process we would like to transport heat or energy potential. I will explain what that means in the next slides. So the same amount of the heat energy that is required to evaporate water is released if water is condensated. That is usually not so easy to experience. But if humid air condensates in water, then again the 680 kilowatt hours per ton water are released. If we use thermochemical fluids to force condensation, then we have the advantage that condensation is not taking place only at the dew point, but at a selected point which depends on the thermochemical fluid. So based on these processes, the aim of the project is to develop 2 basic new devices for district networks. That's first an absorber and second an desorber. So in the absorber, we use moisture air, cold air that is coming in. Absorption takes place in the absorber, heat is released from that process, and we get hot, dry air in the end. So if we have done so, then the thermochemical fluid is diluted by the absorbed water, and we need to regenerate, to renew the thermochemical fluid. And that is done by heated air, usually heated by excess heat from industry is the intention. With that heated air, the water from thermochemical fluid is removed again, and we have concentrated thermochemical fluid that can be used again for an absorption process. Okay, so that's the basic 2 processes taking place in the network, and the aim is now to provide services based on these processes. So services are drying, heating, and cooling that we aim to provide by this technology. I will go through them now in detail. So drying, industrial drying, that's the easiest process to be provided by absorption. So we just need to take the humid air in the absorber to remove the humidity and to provide the hot, dried air again to the drying process. And the advantage is that it can run in air recirculation, and we can avoid a lot of primary air energy consumption usually required for drying, because we can base the drying process on the absorption, which is then driven by excess heat at other locations, other times, that is transported by the network. One further interesting aspect is that the thermochemical fluid is able to stabilize humidity very good. So if we have a certain concentration of the fluid, then the relative humidity is fixed by approximately ±5% to that humidity level if the air is in contact. And for we can use this potential, for example, for stabilizing humidity for indoor spaces or for processes that need fixed relative humidity. Okay, let's move on. Yeah, what is also developed in the project is some kinds of nomograms, of diagrams where you can quickly examine if we have some temperature level and what kind of concentration you need, what kind of humidity of the air results from that, and what is the energy transfer from that. That will be ready very soon and be published. So that allows you to select cases and to check if the technology is able to supply these cases. Let's move on to heating and heat recovery. That is a bit more complex process. But basically it's also using the absorption and the heat release in the absorption process. First, we can use humid air from an external source. That can be a greenhouse that provides humid air and acts as a humid air solar collector in that situation. And the humid air is coming into the absorber. Absorption is taking place. We again generate hot, dry air, and that air can be used for heating the building. I have to remark that the temperature lift is limited, so that is mainly interesting for low energy, nearly zero to energy buildings to be used. At the same time, we can do heat recovery and also latent heat recovery, which means that we recover the energy that is captured in the humidity of the air that usually would go out. So usually if you have a swimming pool, it's a good example, you have to ventilate the room in the swimming pool to remove humidity. What you can do with thermochemical absorption is to remove the water from the air above the swimming pool, and that allows you dramatically to reduce the ventilation and with that the energy losses. So it's heating and heat recovery which can be provided by thermochemical absorption. Yeah, cooling. Cooling requires also some steps to provide cold air in the end. The first step is that hot outside air comes into the absorber and humidity is removed from the air. That causes, the absorption process causes again an increase of the temperature above the temperature level outside. That allows us to do heat rejection to the outside. And if we have again the temperature level of the outside but dry air at that point here, then we can do evaporation and provide air that is below the outside temperature level. That can be done without any support of compression cold, but also the combination with compression cold is interesting because usually you cool down ingoing air by compression cold to the dew point to remove humidity. That requires a lot of energy consumption. And in that process, based on absorption, you can avoid going down to the dew point and run, for example, a compression cold source instead of the evaporator at a much better COP. Okay, so that are the three services. Yeah, we have demonstration for these services that is currently under development in Berlin. That is the two boxes, absorber and desorber, humid air solar collector, one prototype, and another prototype building that will integrate parts of the technology in Berlin. And that is a scheme of a laundry drying process in which it is also intended to test absorption for the removal of water from the drying process. Okay, so let's move on. So we have now the three services. If they are provided, the result is diluted thermochemical fluid, and now it's required to concentrate that again. As mentioned, that is done or is possible by low temperature excess heat from industry, but also from renewables, for example, from solar thermal sources in summer or something like this. And as a result of the process, we have concentrated thermochemical fluid again. One interesting detail is that we can use cooling fluids as well as air for the regeneration process. So we can also utilize air at the temperature level, which is, for example, available from data centers, and that is usually difficult to use or to exploit the available excess heat there. Yeah, what we expect that is possible is that we tap this unused potential. So in conventional district networks below 8 degrees centigrade, it's at the moment with the current technology not so easy to use that. And but if you look at the excess heat available, that is more than or approximately 50% that is in that temperature range. And what we would like to do is to do regeneration in that temperature range and use the upper temperature range either for high-grade desiccants for regeneration, high-grade thermochemical fluids, or for other conventional technologies, so that we achieve a better exploitation of the available excess heat. There's also supply-side demonstration how to access excess heat. In Zurich prepared. This on the left there are running plants for heat recovery using open absorption locally in plants, heating plants in Buch and Berlin and at the German Sport University in Cologne. And in the project there will be a demonstrator applying the technology to use excess heat for regeneration from a CHP plant and utilizing that for drying purposes. So to form a network, we had the two sides, supply side and demand side. To form a network, basically the process looks like shown on that slide. So we have diluted desiccant coming in here for the regeneration. We have air and we have hot air removes the humidity from the desiccant, so that means 1 cubic meter is coming in. We remove the air and 0.25 cubic meters of water are removed as vapor. 0.75 cubic meters concentrated fluid goes through the network, are available for on the demand side, and then a process of absorption is taking place. The vapor from other processes is coming in, absorption provides heat, and the diluted desiccant is going back again to the supply side. So to summarize, the aim is to form a thermochemical district network on that basis with different services provided on the demand side, and space heating, heat recovery. We have the drying processes, industrial drying, humidity removal, or set point humidity, and we have space cooling in buildings or other processes. And in the middle we have the heat source with the regeneration and also with the thermochemical storage. And the advantage is that we can form a smart multifunctional network, that we can utilize low-grade heat for the regeneration and support or couple that in other processes to allow heat cascading and utilize the low end of the heat cascade. We have no thermal losses in the transport and in medium and short-term storage, so that allows us to have large transport distances. And more than 50 kilometers should be possible. And we have a higher energy density compared to water networks because of the high energy in the thermochemical process. So it depends a bit on the temperatures in the water network, but you can have 3 to 8 times as much capacity in thermochemical network. So 200 to 300 kilowatt hours per cubic meter transported thermochemical fluid is the usual capacity you can have. Yeah, and what is also interesting that we can operate at different temperature levels. So regeneration in the middle can take place at a lower temperature level as, for example, industrial drying. So we can regenerate at 30 to 40 degrees centigrade and then have industrial drying at 80 degrees centigrade, which is not possible in a usual heat cascading way. Yeah, so I hope that gave you a short introduction to the thermochemical technology. We are also operating with demonstration, but also with case studies and simulation to develop, to examine the potential of the technology and also develop control strategies. But that I would postpone to future presentations, the details on that. So thank you very much. Questions are welcome.
Thanks a lot, Philip. I think that is very interesting approach, very innovative. If I understood correctly, you have basically one supply line with diluted solution and one return line with a concentrated one. And one question we received is if you already made some calculations on the pressure losses that you have on the pipelines compared to water, water medium, I guess.
We have no detailed calculations of the pressure losses right now, but we have made some estimations what will happen. So there are some important differences between the two technologies. First, the thermochemical fluid has a higher viscosity than water, that is clear. So that will increase pressure losses, pumping power a bit. But on the other hand, we have the higher energy density in the network, and that will reduce again the losses. And we approximately expect that the both pressure losses and pumping power and so on stay at the same level as it is now. We have to deal a bit with the fact that we have open systems, and that requires a bit different structure of the network. So we need decentralized pressure pumping, setting under pressure. That's the detail, but that has to be solved in future.
Okay, thanks a lot, Philip. Again, I would end over.
About this question, so Serena Danesi from Zurich University of Applied Science. So we have to think that the salt solutions, the concentration is also not very high. So when we have concentrated solution, we have concentration maximal of 50%. That means after we work with concentration 40%. So it's not, so we transport water and salt together. So salt solution is not only salt or brine.
Yeah, that's exactly right. On the diluted side, the viscosity becomes similar to the viscosity of water.
Okay, thanks both. Thanks, Serena, for this detailed suggestion or description. There are a couple of more questions, but we need to go on further with the presentations. I ask please Philip and Serena eventually to answer in the text box to the two questions that you see by Dirk Petrushka and David Leinfelder. David Leinfelder.
Yeah.
Okay, and then I would hand over to Dirk for the next presentation. And I ask you, Dirk, to really stick to the timeline, or even try to reduce a bit the time for your time for the presentation, if you can. And you have to unmute your microphone, please.
Okay. Well, thank you very much, and good morning, everybody. I'm really happy to be involved in this nice workshop and to talk a bit about our control developments in the FLEXYNETS project. So I'm from the company Inesys, who is developing the control issues, which I will present now. Okay. So, sorry, I can't move the slides.
You should be able. Otherwise, you can use the arrows just behind your.
Okay, so I try to use this.
Okay.
Okay, no, it works. Okay, so Roberto mentioned already about the FLEXYNETS concept in general, so that we want to connect different sources and things in a low temperature or very low temperature network, which means that we have to integrate and interact and to implement an intelligent interaction and control of multiple consumers, prosumers and suppliers in a cold district heating network. Because we don't have a classical network in this stage as we had before, so we are faced with a problem that we have a transition in thermal networks, not only in the electricity grid but also in thermal networks in this case. So coming from the classical district heating system, this was one-dimensional with one heating source and a lot of consumers connected to a heating network. This is now also transferred to a kind of a prosumer network where we have not only one supply station but also consumers, which are sometimes also acting as providers of heat or cold, and they are distributed within the network, which makes the control of the overall system much more complex at the end. So what is a problem? So we have one, so here called ring structure, and we, connected to this ring structure we have different storage possibilities. We have buildings which require heating energy for domestic hot water and for space heating, and they are typically connected to this low temperature heating network by heat pumps, which increase the temperature from the low temperature side to a higher temperature level, which is required for heating and hot water generation. We can also connect chillers or the waste heat from the chillers to such a network. So we are rejecting the heat from the chillers by using the thermal network. So here we feed in heat to the network, here we take out heat of the network. And there can be different sources connected, also waste heat from industry, solar thermal sources, which feed in at different points of the network. So this shows that there's quite of a complexity already within this thermal network, and balancing such a network needs some specific control features. And this becomes even more complex if you also consider the electricity network and the sector coupling between electricity and thermal energy, where we have at the generation side, when we have a cogeneration system, for example, which provides electricity and heat is fed into the network, and electricity is also produced, and we have the same case for other GHP units connected to such a network, or by the chillers also consume electricity, and by the heat pumps who consume electricity by providing heat. So there's an interaction between all these systems, and we can use this local flexibility in these different sectors, which are mainly provided by thermal storages, heat or cold storages, and by intelligent control we can control these systems in a way that we support the needs of the electricity grid. So when there's a lot of renewable energy in the grid, electricity grid, then we activate these systems and use electricity. When there's less renewable energy, then we live more or less from the storages on the different sides. So there's also this coupling to the electricity network. And we can also go far further if you have GHP units operated with a gas network. We have also a kind of an interaction with a gas network. So at the end we come up with a multi-level control optimization problem. So we have the local optimization in each of the single buildings connected to the heating networks. They need, of course, to provide the heat required to keep the temperatures at a certain level. And so to do this, there's a local optimization between the storages and the room temperatures. So this is a local system. Then they are connected to the network, and we have, of course, some heat supply, because the different sources are not always equalizing the needs of demand. So we need also have some centralized sources which can be connected to equalize the demand and supply. And we have also some storages where we can store excess heat in the network. So this is the network balancing, so where we need to keep the network in an operational situation so that it always can provide what is needed at the different stations, substations. And if we integrate again the electricity network and the gas network, then we have another optimization level where we want to provide services to the electricity grid, or to use electricity when it's cheap, also gas when it's cheap. This is more or less the strategic optimization level which we need to address in such a complex system. Now, in FLEXYNETS we are developing control systems which are able to cope with this high complexity, and we subdivided the control in different levels. So we have the substation level, which you see down here, where we have the single controllers of the different devices in the single buildings, and also supply stations within or distributed over the network, and also the consumers or prosumers in the network. They are all locally controlled by controllers, which need to ensure that the needs are covered. We have also control of storages, which can be in the single buildings, or which could be distributed over the network or centralized. So they all need to be controlled by local controllers. So this is quite modular, and at the upper level we have a high-level system controller, which has mainly the task to balance the overall system, so that in order to always ensure that enough energy is available in the network. So this can be done also first on a local level, seeing what is happening in the network, and then reacting on temperature levels. But this can also happen on a more strategic level. So if I integrate, for example, electricity prices, gas prices, weather forecast data, so I know what my demand will be by predictions which can be implemented, and then I can develop a better strategy how the system could be operated in order to maximize, for example, renewable sources in this network, and this is all done in this management or strategic control level. From here, the high-level control gets operational schedules for each of the single devices in the network, and these are then transferred by the high-level control system to the single sub-devices, which then try to follow these schedules as long as possible. So how do we come to this optimized control? So we are using simulation tools, of course, on the first hand, to test on the one hand the control of single substations, which are also quite complex if you have prosumer stations which provide heat and take heat from the network. So these are then built up in simulation models. We have models to demand, and then we have a control strategy which is implemented in these low-level controllers, and this can be tested in a simulation environment and optimized before it is really brought on site and installed. So this is an optimization of the more or less low-level control strategy. Then we have also some more advanced tools which we are going to use. This is a model-based predictive control. We have models of the buildings and of the systems installed, and we have control strategies which we are going to follow, or schedules for the operation of the different systems, and this can then be optimized in an optimization loop to find the best and optimum operation of the overall system. So this is quite simplified shown here. It's rather complex in reality, but we are trying to cover some of these issues within our project as well. So how are we operating on the installation side or on the controller side? So we have, as I told before, we have substation controllers in each station, and this can cover also some sub-device controllers for the single devices within each substation. And this controller is then the master of these sub-devices of the station level, and is responsible to operate these systems in an optimized manner. And this is then connected also to a web interface where you can enter this controller and see what happens there, and also change schedules. And it is also connected to the higher level control. How is this control system structured? So the control code is more or less a C code in each controller. We operate with the same code. This code has different levels for different types of applications and systems integrated in the control of these systems. And we have an initialization file which then decides which components are really available at which controls substation, and then only these are activated and combined to a control system. So it's quite modular, so that we are really flexible in motivating on changing the different issues and adapting it to different possible substation situations. At the end we will have different substation controllers which are responsible to control the different substations and also the supply units within the network. And we are developing, this is also a kind of development work which we are doing now, to develop this high-level controller, which is the overall master of all the single sub-device controllers, and which is then responsible to balance all the network centrally. This can be, this is then connected to this supervisory strategic control, where these control strategies are developed using weather forecast data and modeling, simulation models of the tools, and from there we get the optimized control strategy, which is then supplied or transferred to the single devices. So this could be in future a cloud service or part of it, at least the strategic control level could be a cloud service, and we have one hardware somewhere in the network which takes the high-level control responsibility.
To conclude shortly.
I'm nearly through it. So we have one demonstration site in Bolzano where we test all these control issues in a laboratory test system with a solar collector, gas boiler as heat sources. We have absorption chillers and ORC units within the system, and we have a network, simulated network here, where different substations, prosumer substations can be connected and controlled so that we can really simulate a real network there. So this can have different operation modes from heating to cooling and distribution. So here you see some nice pictures of this demonstration site, which is installed in Bolzano quite recently, and it's already in operation now, and we can now start in testing the different control strategies on a laboratory level. So that was all from my side, and I'm happy to answer questions if you have some.
Thank you, Dirk. As we are a bit late, I would hand over directly to Johan for the next presentation. And in the meantime, if any question comes in, we will address it later before the end of the webinar. So, Johan, you have to unmute your microphone, probably.
Yes, okay.
Okay, we hear you. Good.
Okay, yeah. Well, good morning, everyone. My name is Johan de Smet. I'm the project coordinator of the Horizon 20 Storm project. And I'm working within the Applied Research Center VITO in Belgium, together under the umbrella of Energyville, which is a cooperation between VITO, KU Leuven, IMEC and the University of Hasselt. During my presentation, I will give you a short overview of the Horizon 20 Storm project related to intelligent control of district heating and cooling networks. Ricardo, can you give me control?
You have the control. Yeah,
okay,
exactly.
Yeah, it works. Yeah, okay, good. So the project is within the context of the fourth generation district heating and cooling network. So the overall goal is the decarbonization of our energy system by making it more energy efficient and by integrating more renewable energy. So compared to the third generation district heating networks, the fourth generation network systems has to cope with uncontrollable production sources, and there's a need also for flexible sources. So what is the challenge then in the fourth generation district heating and cooling systems? Well, one of the challenges is to make them ready to deal with uncontrollable or fluctuating production of heat and cold, which means, for instance, that if, for instance, a large solar thermal field is coupled to a district heating system, we have to cope with the sun not shining every day when we want the sun to shine. However, district heating and cooling networks are demand driven and they are not production driven, so the production always follows the demand. And the main question there is, how can we make a network follow the fluctuating productions then? Well, there are some solutions, and first the solution is we influence the demand, and then by influencing demand, automatically the production will follow, as you can see on the graph there. And the second solution is just to decouple demand and the production. So if we decouple demand and the production will also follow the demand. So both of these solutions, influencing the demand and also decoupling demand and production by, for instance, using thermal storage, is the main target of the Storm project, and is also the main scope of using flexibility in the network. So which solutions or which natural flexibility is available in district heating and cooling networks? Well, first of all, we can use the thermal mass of buildings. Thermal mass of buildings has a high capacity, and buildings can be used as thermal storage buffer. The second one is water in district heating network pipes, so in large district heating network systems. For instance, in the network of Heerlen in the Netherlands, we have around 700 cubic meters of water that is available as a thermal storage buffer. And third alternative, we can use physically thermal storage buffer system, so large buffer storage system. So we can make use by using this thermal buffer system as a flexibility of the system. To activate this flexibility in the network, in the buildings, or by physical buffers, we need to have an intelligent controller. And this is where the STORM project is working on, activating this flexibility. So the STORM, some general info about the STORM project. So the title is STORM, which stands for Self-Organizing Thermal Operational Resource Management. And the aim is to demonstrate a generic district heating and cooling controller based on self-learning optimization techniques. The project started in the 1st of March 2015, and it will run for 42 months, so we are now almost over halfway. It was submitted to the Horizon 20 EE13 call, which was mainly focusing on technology for district heating and cooling networks, and it was also a research and innovation action. So we are the same a little bit as the previous project. We are with six partners, a budget around 2 million euros. On the one side we have VITO, which is the Applied Research Institute, which also is the project coordinator and was also developing the algorithms. We have NODA, which is a small SME company in Sweden, specialized in smart district heating, controller and intelligent control of buildings. And then we have two demo sites. The first demo site is the demo site in Mijnwater, Heerlen in the Netherlands, and the second one is a VEAP demo site in Rottne in Sweden. I will give you from these two demo sites some more information. Besides the technological development and the implementation of the controller in real networks, there is also a dissemination activity which is done by Euroheat and Power. And furthermore, in order to increase the awareness of intelligent controller, we also have the Zuid Hogeschool from Heerlen, which is responsible for the educational packages and training packages for professionals. So with 6 partners in the consortium. What are the objectives of the project? Well, first of all, we want to develop a generic controller for district heating networks, and our controller can also be applied in cooling networks. We want to demonstrate the generic controller in these two existing district heating network systems. Furthermore, we want to quantify the benefits, so we want to know what is the real value of applying an intelligent control, for instance, on the OPEX of district heating and cooling systems. Furthermore, we want to develop some innovative business models and also increase the awareness by setting up some educational and professional training sessions. And we want to ensure the market update, so we are really looking at the replication potential of such a controller. What I mean by generic is which means that it has to be able to deal with a variety of networks, not only the 4th generation or even the 5th generation networks, but also the 3rd generation network. This is guaranteed by a number of features, so we are within our optimization algorithms. It is developed as an add-on to existing network controllers and SCADA systems, which means that our controller can be integrated in these network systems, but also can communicate with these SCADA systems. It's based on self-learning algorithms, and it applies that we can apply multiple control strategies and also use multiple storage technologies. Okay, which control strategies do we apply in the project? Well, there are 3 control strategies implied. First of all is the peak shaving, the second one is the market interaction, and the third one is the cell balancing. The first one is the peak shaving strategy. So this is mainly operated for typical networks with small sustainable energy sources and a larger fossil backup. So there we want to eliminate, for instance, a fossil fuel boiler in an existing district heating system. The market interaction is when we have, for instance, cogeneration units of heat pumps, which can operate simultaneously on the electricity market, and depending on the electricity prices, these equipments, the heat pump and the cogeneration units, can be switched on or off depending on the electricity price. The third control strategy is more related to cell balancing, and cell balancing, which means, for instance, to have an increase of the energy efficiency, which means, for instance, that if different district heating networks are coupled, the energy from one network can be transported to the other to increase the energy efficiency. So these three control strategies are developed within the STORM project. So as I said, we have two demonstration sites. So the first one is the demonstration site in Sweden, in Rottne, in Veckrö. And this is an example of a typically third generation network, which composes of two wood chip boilers and one biofuel oil boiler. And design temperature is 90 and 60 degrees. So the aim of the STORM controller there is to eliminate the operation of the peak fuel boiler, and then of course reduce the operational cost of the network. Our second demonstration site is in Mijnwater, Heerlen in the Netherlands. This is an example of a highly innovative fourth generation networks which is operated at very low temperatures, ranging from 28 degrees to 16 degrees. The heating and cooling is provided in the buildings to heat pump systems, and the Mijnwater system is coupled. So the whole district heating and cooling system in Heerlen is coupled to an underground mine water storage system of large volume of cubic meters. The objective there in Mijnwater is to balance the heat and cold from the producers and also the consumers. So there we want to apply the cell balancing technology. What we did so far was the implementation of the controller algorithm. So we made three models: a forecaster, a planner, and a dispatcher tracker. So in the forecaster, the goal of these forecaster algorithms is to forecast the energy consumption of the whole district heating network system. So we use there machine learning techniques. So these techniques learn on the data they receive. So the more data they get, the more accurate they become. And the input is time, historical consumption, outside temperature, and the output is the future energy demand per hour or per quarter for the next 24 hours. So what is the status of this implementation? Well, we developed the forecast algorithms. They were developed. We pre-tested them in the district heating system in Rottne in Sweden, and they are now implemented on the NODA ICT platform, and they are running in the Rottne district heating network system. When we have the forecasting of the energy consumption, and given of course the control objectives, the aim is of course which optimal consumption profile can be achieved, taking into account the forecast. So the aim is there. We have the input is the forecast consumption. We have a cost function, and the planner will give us an optimal consumption profile. So the status there is that the algorithms has been developed and are now implemented also in the software environment. Then the third option is the feature is the dispatcher tracker, and this functionality is when we have the forecasting and we also have the planner, we try to follow and track the proposed energy consumption as much as possible. So this means, for instance, that the tracker of the planner says, okay, the maximum peak amount is 2.7 megawatt, and the dispatcher tracker will then send signals to the different equipment production units and also to the buildings in order to achieve the 2.7 megawatt. What is the status now of the development Horizon 20 STORM project? So we are more than halfway. The version 1 of the controller is developed and is implemented in Rottne and also in Mijnwater demo site. So there we focus purely on the peak shaving feature. The version 2 of the controller is in development, and this will be implemented before the heating season 2017-2018, and this compromises the market interaction and also the cell balancing options. So we are now, I said, more than halfway, so we are now evaluating the performance, so the energetic performance, also the financial performance and of course the ecological performance of the Storm version 1 controller. And these results will be soon made available to the different channels, Twitter, LinkedIn, and also on our website. To give you some more information, there is a paper on the operational demand forecasting in district heating and cooling systems, which was presented at the 15th International Conference on District Heating and Cooling Systems in Seoul. So I hope that this short presentation gives you a small overview of the Horizon 20 project Storm.
Okay, thanks to you too, Johan. I don't know if there are any direct questions from the audience. Otherwise, I will go with the last presentation and go through the questions at the end. Okay, it seems there are no questions yet. So I will start my presentation and I'll try to be in time as the other did. Thanks to all, by the way. So yeah, I'm going back to my last point in the previous presentation, the first presentation. So we have a lot of different technology solutions. We have seen a lot of different technology solutions and control solutions that can be put into place in this to operate this kind of low temperature district heating and cooling networks. Again, the main topic of all the presentation you have seen this morning was the multiple energy sources available. And then from the technological point of view, we can do it, so to say, but then the next question is, can we economically integrate these sources into the network, and which are, by the way, the sources that are more suitable from the economic point of view. And then again, at which price the utility should buy, for example, renewable heat or waste heat from different sources. And when we start to think of this, we understand that we can bump into a number of different business models, because again, we move from the third generation solution of networks, where we have a structure one-to-many, one thermal plant distributing energy to the customer, to all the customers, into we are moving to a structure where a many-to-many structures, so where many producers can provide energy to as many customers, so to say. Plus again, if we use heat pumps, as in the FLEXYNETS project, for example, the final customer needs to buy both thermal energy from the network and electricity to run the heat pump, the substation. And therefore, again, here a number of possible business models rise. So what we are trying to do in FLEXYNETS, in parallel with the technical activities, is to work on the on structuring all these possible combinations, all possible business models, and try to go through them with say some practical examples and see how thermal energy and electricity can be what the price of the different energy sources can be, how the price of the different energy sources can be decided, depending on the business case. For example, to make some examples, for example, if you are an energy producer like an industry, you can, as a producer, you can set up your to connect to the network, and then the utility would pay the thermal energy that is fed into the grid. But there are other possibilities, like when you are a data center or a supermarket. In this case, for example, we might think of the utility company directly setting up a substation to connect to the dry coolers of the of the building or the service, and to take energy, transfer it to the feed it into the grid, and then again it might be that the thermal energy fed into the grid is not paid by the utility, because say the supermarket or the data center, they can have a direct benefit by having lower evaporation temperatures at the dry cooler, at the condenser of the refrigeration cycles or the air conditioning cycles. On the other hand, if you are a consumer, you might buy electricity to run the heat pump by your usual energy provider, or it might be that the electricity is paid by the utility itself, and then the utility makes a price for the heat that is sold to the final customer, that is taking into consideration both thermal energy and electricity consumed. These are not what you see on the screen are not all the combinations, just a few. And by the way, some customers can play the role of a prosumer, because they can in sometime buy energy or draw energy from the network for space heating, for example, or domestic hot water preparation. But for example, residential customers or tertiary customers, they can sell waste heat out of air conditioning of the buildings during summer to the network. So actually they can play the role of the consumer or the producer, depending on the time frame. And again, this say produces new combinations and new possibilities. So what we are trying to do is to basically look into what business model can be put into place, as I was saying, and to do this, we decided to approach the problem from with a top-down study. And basically, what we did is to look into how much a final customer pays. For example, in this case, for space heating, QH is the demand of the building, space heating, heating demand of the building, and the total cost for heating of the building is what you see on the right. And what we said is that when you connect to the network, the final customer cannot pay more than this reference price for heating the building. And again, when you connect to the network, the price the final customer pays is a combination of the electricity price to run the heat pumps and of the thermal energy that is taken from the network. All these numbers are known, apart for the cost of the thermal energy that is taken from the network. And again, in this way, basically, with this calculation, we can understand what is the maximum price the utility company managing the network can make to the final customer. Turning the equation into a graphical representation, this is what you get. The two charts represent two cases where we have a seasonal COP of the heat pumps, the customer heat pump, moving from 3.5 to 6. And again, based on the reference heating price that you read on the x-axis and on the electricity price that is represented with the lines here in the network, you can understand what is the maximum energy price to the network that the utility can apply. For example, if you have a typical European gas price of 100 euros, the actualized energy cost for heating, reference energy cost for heating, including also investment and maintenance and running costs for the gas boiler, can be valued something like 140 degrees. And then if the customer pays something like 15 euro cents per kilowatt hour to run the heat pump, then what we see is that the price for the maximum price that the utility company can apply to the customer is again in the range of 130-140 euros per megawatt hour in this case. Oops. So basically, this is the price from the utility to the customer. But then looking into how much the utility company pays to harvest and to distribute the thermal energy to the customer, then we can calculate basically what you see on the x-axis, which is the income for the utility company for the thermal energy delivered. And again, you can see that the income for the utility can range in a large span depending on the cost price, annualized cost of it. Sorry. Here we have again some parametric lines that represent cost of the heat harvested and distributed in the range of 30 to 130 euros per megawatt hour. And again, you can understand that the situation for the utility or the remuneration for the utility can range quite a lot. The next step for us was to really look into some example and understand if actual costs are in the range of 30 or in the range of 130. And here I reported a couple of those calculations. They are not exhaustive. They do not want to represent the entire European, say, scenario, but they are just, say some average solutions, average scenarios that can be found over Europe. Then anybody, again, the idea of this presentation is to show a methodology. Then everybody should apply his own number or her own number to the calculation. So again, here we look into the situation where we have a medium-sized supermarket with a refrigeration cycle that waste into the environment 150 kilowatts. And again, the idea here would be to have a substation, including a high heat pump, connected directly in parallel to the dry coolers of the refrigeration cycle and raising the temperature from 25 to 40 degrees. And then this 40 degrees, thermal energy is fed into the grid. Here, from the financial point of view, the investment is borne by the utility company. So there's no economic burden on the supermarket. In this calculation, what we do is to consider something like 1,500 euros per kilowatt hour for the substation with a capacity of 150 kilowatts, as I said, which results in an investment cost of around 225,000 euros, and which corresponds again over 20 years to an annualized investment of around 320,000 euros. And here again, we try to draw two scenarios. One in which the refrigeration cycle works full speed or full power, full capacity for 3,000 hours a year, and the other, scenario where the refrigeration cycle works at rated capacity again for 6,000 hours. For you to know, refrigeration cycles for healthiness reasons, they operate full speed almost 24 hours 7. If there is no, wise, optimized management of the thermal or the electric consumption in the supermarket. Here we consider a seasonal COP of 6 for the heat pump, injecting or feeding thermal energy into the network, and a cost of the electricity paid by the utility, once again, to run the substation of 10 euro cent per kilowatt hour, or 100 euros per megawatt hour. Basically, the cost of energy following the annualized cost of energy following this is in the range of 1836 euros with respect to the investment only. And again, it is around 17 euros for what concerns the electricity consumption, coming from a seasonal COP of 6, as I showed you before. Therefore, if we sum up the two contributions, so the investment cost and electricity cost, the overall cost, the total cost for the thermal energy harvested into the network is in the range of 35 to 52 euros per megawatt hour. So again, something which is in the range of typical thermal energies generated by gas boilers over Europe. Indeed, if you do not need to use a heat pump to feed thermal energy into the network, you operate with a better performance, and this could be done if again the heat from the dry cooler is taken at 30 degrees instead of 20 or 25. And if the network operates at lower temperatures, for example, instead of operating at 20-25 degrees, if the network operates at 10-15 degrees, then you can feed directly thermal energy directly into the network with an heat exchanger without any heat pump in between. And then the investment cost, the capital cost, is much lower, and the seasonal COP, say calculated in this case as the thermal energy divided by the pump's consumption, electricity consumption, is much higher, in the range of 15-20 easily. And then, as you can understand, the total cost of it is in the range of 15 to 20 euros per megawatt hour, as compared to 35-52 of the case before. This said, basically, once we, if we come back to the chart before, or to the charts before, the incomes of for the utility company is in the range of, again, 90 to 100 euros per megawatt hour. We didn't look into the renewable here, but for example, if we look only to solar district heating cases, in their market they have cost of the solar energy fed into the grid, into the network, in the range of 3 to 4 euro cents per kilowatt hour, so 30 to 40 euros per megawatt hour, which is again in the range of the numbers of the values that I showed you right before. We are trying to understand even, say more complicated solutions for integrating solar energy, in which we use high temperature solar and try to produce both thermal energy and electricity via an ORC unit. We are actually working now on defining what are the costs in this more complicated, the energy for the cost for the energy generation for these more complicated solutions. This would be a very rewarding, say, solution for utilities, but actually this is not the entire story, because this takes into consideration only what is needed to harvest the energy into the network, but does not include what is needed to deliver energy to the customer. And in this case, as the customer substation uses a heat pump and a storage, the capital cost, the initial capital cost, is much higher compared to traditional district heating substations. And as you can see here, here we have Another example with a small multifamily house with 10 apartments, fitted with a specific heating consumption in the range of 50 kilowatt hours, space heating consumption in the range of 50 kilowatt hours per square meter a year. And again, what we do is to basically rise the temperature from the network level in the range of 20 degrees to up to 50 degrees for domestic hot water purposes. Again, here some numbers: 50,000 euros the entire the initial capital cost for the building, which is around 5,000 euros per dwelling, and the annualized investment in the range of 81,000 euros. Seasonal COP 5, and in this case we accounted for the final customers paying the electricity bill separately from the thermal energy taken from the network. Without going into the details, the final annualized investment cost for the connection of the network of the multifamily house to the network falls in the range of 70 euros per megawatt hour, and this has to be added to the cost for harvesting the thermal energy. And again, if we come back to the graphical representation, we started from this position here, only when taking into consideration only the energy harvested, and if we cut 70 euros, basically the 70 euros I showed you in the previous slide, then the incomes for the utility company drop down to these kind of levels, which is again in the range of 20 to 30, 40 euros per megawatt hour sold to each of the final customer. Again, in this simulation, in this scenario that I showed, we consider that the electricity is paid at a relative high price by the final customers, but in the end it might be that the utility pays for the electricity, and then the electricity price is better, is much better than this. For example, in the Netherlands, I know that they have high users or large users electricity prices in the range of 5 or 50 euros per megawatt hours, and then we would move up to here, and then basically the remuneration of the investment would shift left in this on this chart in the range of 50 euros per megawatt hour sold. So again, as I said before, this is not a full picture of what could happen in Europe. It doesn't mean it was not the meaning or the aim of the presentation. The idea was to show you the methodology we are using to calculate the financials of the network and the business models and possible business models for this kind of networks, and to show you some ranges in terms of cost and prices to be applied to the thermal energy sold. And here are some conclusions, which is basically that gathering waste heat and renewables is economically viable for this kind of networks. Obviously, better performances are obtained if the utility companies paid all the electricity consumption, because the utility can have lower electricity prices. Obviously, depending on the temperature level of the energy source, the cost of the energy made available can vary largely, as you can see as you could see on these charts. And again, one main good proposition of this kind of solution is that since we need limited investment costs for each of the customers, which are in the range I showed you of some 100,000 euros, then this kind of there's no need to have a long-term plan for investment plan for the utility company to set up a large thermal plant, as in third generation solutions. And again, the single investment can be placed, can be borne by the single customers even. We can think of a solution, again, as I said before, of a supermarket paying for the buying the substation and installing the substation to connect to the network, and then a utility company that remunerates the supermarket for the thermal energy that is fed into the grid, into the network again. What I showed you is an analysis that has been used, that is being used for the decision-making process, but the idea is to use the same analysis for decision makers to decide on eventual incentives that can, say, push the technology on the market, even though we saw that it is not in principle needed. And again, as we saw before, in both control, presentations, we need to, in this kind of, say, networks, we need to couple somehow the energy production and utilization to the energy prices. And again, these kind of tools, could be very useful to be used directly into the optimization process of the control strategy. That's it from my side. Again, I think I was not full exhaustive. At least I hope you got a bit of an hint of what we are doing, and how these kind of tools could be used. It is 12:04, so we exceeded the time, but again, I would like to invite you to ask questions if there are any, and we will be glad to reply to you. This applies to this presentation, but also to the previous presentations. Okay, it seems that there are no further questions for us. As I said, I saw some good presentations this morning with some ideas for new developments. I think the presentation, the solutions that we presented this morning are, move or span from the research level to already the market level in some cases. Therefore, I think we showed where research and where the market is moving with respect to these district heating and cooling solutions, and probably I believe we gave a view on the future situation of the market. That's it from my side. I wanted to thank the speakers for attending and spending their time in this webinar. I wanted also to thank all the attendants to the webinar. And obviously, if anybody has any questions coming out in the next hours and days, please feel free to contact us by email or by phone, and we will be glad to follow you in the next days. Thank you again, and I will close it here and wish you a good continuation of the day and the week.